Hi everyone! In this lesson, we will continue to talk about limits of integrals and sums. A series of numbers, or an infinite sum, is defined as a limit of the partial sums. That is, we defined Sn to be the sum of ak from 0 to n, and then treat Sn as any other sequence with a limit. The geometric series is a classic example denoted as written here. Sn, in this case, is this well-known formula. By analyzing the limit, we see that the sum converges when the absolute value of a is less than 1. Since we are basically dealing with sequences, we inherit some arithmetic properties when applied on Sn. We inherit the sandwich and the pizza theorems, only in this context, the usage is a bit different. If you bound a series ak by a convergent series from both sides, then ak also converges, given the limits agree. This is an application of the sandwich theorem on the partial sums sequences. When ak is bigger than bk, which diverges to plus infinity, ak also diverges to plus infinity, and similar for minus infinity. For positive series, we have an even more convenient tool for which the actual limit is not required. It is known that if a series converges absolutely, then it is convergent. An additional useful tool is the limit comparison test. If the limit on the left exists and positive, then the series A and B converge or diverge together. The best practice here is to find an easy B series for which the limit above exists and positive. Then we can test the convergence of B instead of A's. Note that in general, we cannot change the order of summation inside the series. That might change the limit. Addition term by term works, and so is multiplication by a constant. However, multiplication term by term does not work in general. Try to find a counterexample. Well, observe this counterexample. A well-known series is the infinite sum on 1 over k to the power of p, which converges when p is strictly less than 1. The resemblance to the integral on x to the power of p is not coincidental, and we will talk about it later. This canonical example allows us to easily compare between series. For example, does that series converge? We compare it with plus and minus 1 over k square, which are known to converge. So the convergence of the series of interest follows. We will note here that ak tends to 0 is a necessary condition for convergence for any series. When the ak's are non-negative, the sequence Sn is increasing. Once we bound it from above, we prove convergence. We want to introduce the concept of lim sup. Since this is a crash course, we will go over the details quite fast. In case you have never seen this concept in your undergrad studies, I would recommend to read about it in your favorite calculus textbook and then return to this lecture. We will talk more about the relationship between lim and lim sup in the additional topics module. For any sequence bk, we defined a new sequence, capital Cn, as the supremum of bk from capital N to infinity. C1 is the supremum of all the members of bk. C2 is the supremum when we leave b1 behind. C3 is the supremum when we leave b1 and b2 behind, and so on. In every step, we have fewer and fewer candidates for the supremum. So Cn as a sequence is decreasing in the weak sense. When bk is bounded, we get a bounded decreasing sequence, so the limit of Cn must exist. Call it L, and define L as the lim sup of bk. If our original sequence has a limit, including plus or minus infinity, then it must agree with the lim sup. In the context of series, this happens most of the time. Now, we can present a few extra tools for non-negative series. For the root test, we calculate the lim sup of the nth root of an. If the limit is less than 1, then the sum converges. If it's bigger than 1, the sum diverges. Otherwise, the test is inconclusive. In most cases, it is enough to check the lim of the nth root of an, since if the limit exists, then it is equal to the lim sup. For the ratio test, we use this limit after we made sure that all the ak's are positive. Those redundant zero terms does not contribute to the sum anyways. Same goes for here. L less than 1, sum converges. L bigger than 1, sum diverges. Inconclusive otherwise. Another tool is at our disposal when the ak's are non-negative and decreasing. In this case, we need to find a decreasing function which obtains the values ak on the positive integers. In that case, the sum converges if and only if the improper integral converges. For decreasing functions, there is a strong relation between sums and integrals. For example, does this sum converge? No. It is decreasing, but the corresponding 1 over x function has a divergent improper integral. By the way, this series has a name, the harmonic series. Let's see a few examples. Try to work out each one yourself and determine convergence or divergence before continuing with the video. This is a non-negative series. Usually, the ratio test works well when dealing with factorials. We get a bounded sequence times a 10 to 0 sequence, so the limit is 0 and the series converges. What about this one? The sum diverges since ak does not tend to 0. For this one, note that from a certain k, sine 1 over k is positive, so we have a non-negative series. The root test works well with something to the power of k. We just need to use L'Hopital to get the limit and the series converges. The alternating series is a special case in which the signs of an otherwise positive terms are alternating. In this special case, the series is convergent if and only if ak approaches to 0 and decreases monotonically. For example, this alternating harmonic series is convergent, although it does not converge absolutely. Quiz. This is a 2.5 minutes question. Stop the video now and come back to us with an answer. Ready for the answer? It is D. Arctangent is bounded, so it is like multiplying by a constant. It does not contribute to the convergence or the divergence. The ratio test gives us the answer. For 2, notice that no x to the power of p function converges on both sides of the improper integral from 0 to infinity. For 3, we apply the root test and calculate a known limit.